Hello everyone, my name is Álisson, and now I will present the work Numerical Experimental Investigation of Cryopreservation Process by Droplet Vitrification. We are from Unisinos University of the postgraduate program in Mechanical Engineering. So, cryopreservation is a process that consists in freezing and storing a cellular sample in extremely low temperatures, about -196 Celsius degrees. It has several applications such as assisted reproduction, disease treatment, genetic enhancement, conservation of embryos, and other biological materials. The current cryopreservation protocols can be classified into groups: conventional or slow freezing with the cooling rates up to 100 Celsius degrees per minute, and fast freezing or vitrification with the cooling rates around 20,000 Celsius degrees per minute. And there is another segment called ultra-fast freezing that have gained greater importance due to the thermal and biological characteristics such as high cooling rates, small volumes of biological material, low CPA concentration, and high viability. Talking about the vitrification, we can define this process as the passage from a medium in a liquid state to a vitrified and amorphous state, without the occurrence of crystallization. There are several methods to vitrify biological materials, for example, OPS, film evaporation, film vitrification, microchannel, directional freezing, and the droplet vitrification method that was used in this work. This method is widely used because of the simplicity of the process, with high cooling rates and sample viability, where it's possible to achieve cooling rates above 10,000 Celsius degrees per second, depending on the droplet volume. We can classify this method in two protocols, by immersion and by contact. The first one by immersion, in the figure of the left, where the droplet is dripped inside the liquid nitrogen, and the second one, where the droplet has no contact with the refrigerant medium. That is good because maybe avoid contamination. Well, the objective of this work was evaluate numerically and experimentally the droplet vitrification method by contact, in order to understand the phenomena involved during the sample freezing, such as temperature curves, cooling and solidification rates. Our experimental bench is composed of a vitrification system with one syringe, one vessel to store liquid nitrogen, and 3 thermocouples of type T. A data acquisition system with one computer and 2 modules of data acquisition, and a video recorder system with a high-speed camera. So, how was our experimental procedure? First of all, we collect water with a syringe positioned on the freezing surface. We used a brass cylinder immersed in liquid nitrogen. The second step, we drip a volume of 20 microliters over a thermocouple positioned on the freezing surface. Our tests were performed by collecting temperature data every 0.01 seconds in order to reduce the reading fluctuations due to the external effects of the experiment. And the video recording of the tests was carried out with a capture rate of 600 frames per second. And we also used the image from the test plane to measure the contact angle of the droplet with the surface, where we found an average angle of 74.51 degrees and a high variation, a standard variation of 11.37 degrees, as can be seen in this table. And we tried to explain this because of the nature of the procedure that was used during the measurements, which was influenced by some factors. For example, the inclination of the syringe, the drop height, which were not controlled during the tests. Okay, here is the numerical procedure. We use the software ANSYS Fluent for the computer simulations. The numerical domain consists in 3 regions: environment composed of air, droplet composed of water with a volume of 20 microliters and a contact angle from the experiment, and the vitrification surface composed of brass. We use the condition of symmetry to simulate only a half part of the domain. We use the variable properties for water and brass, and we consider the sides of the substrate with thermal insulation. Here we use the ANSYS Mesh software to create the computational meshes, applying the GCI method to evaluate the mesh independence. So we created 3 meshes with a refining ratio of 1.5 between them, using as a reference parameter the liquid mass fraction, and we find a value of GCI of 0.22%. That's a good value because according to the literature, values below 5% are acceptable. So we create a setup to simulate 20 seconds with a time step size of 5 milliseconds. We use the laminar viscosity model, a simple method of discretization to solve pressure velocity coupling, a second order algorithm to solve pressure, energy, momentum, and transient formulation. And as the convergence criterion, we use the residuals and the number of interactions per time step. These are the governance equations that the software is fluently used to solve the solidification model. So the energy equation described in terms of enthalpy, continuity, momentum, and the source term, where beta is the solidification parameter and A much is a constant to predict the interface liquid-solid during the solidification process. Here we have the numerical experimental results for the solidification process. The total droplet solidification occurred in less than 10 seconds. We can see this through the contour and the graph of the water liquid mass fraction. We can analyze the solidification process through the comparison between the video of the numerical procedure and the experiment. And it's possible to see a good agreement between them. It's important to say that it would not be possible to achieve this curve experimentally in our tests. So the numerical simulations, it's a powerful tool in this case, and comes to corroborate with the experiments when we have this difficulty. We can also explain the vitrification process using the temperature as a parameter. So here we have the temperature contours for the numerical domain, and here we have the graph with the comparison between the numerical and the experiments. And it's possible to note a difference between the pattern of the numerical and the experiments performed. And in relation to the cooling rate, we found a good agreement between the curve 1 to 4 with the numerical results, with a relative difference around 0.33%, but for the curves 5 and 6, we found a big difference, more than 30%. And we can explain this because of the height of the temperature measurement and the contact angle variation. In this case, we found more than 11 degrees. In order to understand this big difference between the numerical and experimental results, we evaluate the temperature dependence in relation to the measurement point inside the droplet. So we divide the droplet in 9 regions and we collect the temperature in each point, as we described in this graph. And it's possible to see here the similarity of behavior between the curves, and we divide this behavior in 4 regions: pre-freezing, stabilization, rapid freezing, and post-freezing region. So, the computational simulation is a powerful tool to assist in experiments with high complexity of phenomena involved, providing detailed information on regions of great interest. It was possible to replicate numerically the experiments with a good agreement between the results of cooling rate for the curves 1 to 4. The expressive difference for the curves 5 and 6 is due to the higher contact angle variation, where large contact angle values provided greater cooling rates and vice versa. Temperature measurement method and thermocouple position, drop height, contact angle variation, and environment conditions can influence the results. And for future works, we pretend to modify the experimental bench and perform more computational simulations, increasing the degree of phenomena involved. For example, humidity, drop height, temperature measure and position, mixing of cryoprotectant substances, and application of cellular materials. These are the references that were used in this work. And we would like to thank to Unisinos, Emocor, and CNPq for their grant. Thank you very much.